First of all, I'd like to thank the organizers, all of them, but in particular Séverine, for inviting me to give a talk in such a nice conference. It is always a pleasure to come to Stier. It's a wonderful place, and the weather is nice, and the people are nice, so what can you ask for more for, right? So thank you very much also for coming here after lunch instead of doing something else, which I totally understand you might want to do. So I'll try to entertain you, I promise. With this, well, we're going to do some math. Huh? So as Matthieu said, actually, Matthieu has a tricky position today because he's the chairman, my chairman, but also one of the co-authors of this result. Don't worry, I have a timer here. I will not go over time, I promise. So what we are interested in this joint work, still in progress with Matthieu and Lorena Lopez-Hernanz, are, well, we are interested in the dynamics. So this, as it was said this morning, this is the dynamical day. So we're interested in the dynamics of, well, we're going to stay in dimension 2. So if you don't like general holomorphic maps from C2 to C2, think about a polynomial map from C2 to C2. And in our case, it will fix a point, and it will be parabolic at that point. Since the dynamics is invariant under changes of coordinates, my fixed point is my favorite fixed point, which is the origin. And parabolic, well, I could be more general, but for the sake of simplicity today, parabolic will mean the differential at the origin is the identity. And of course, I want to do, well, dynamics, which has a meaning, and so there is a map that I'm going to exclude. Can you guess which one? I'm going to exclude the identity, okay? I will take a non-trivial endomorphism of C2, which fixes the origin, it's tangent to identity at the origin, but it's not the identity. And actually, what we are going to do is we are interested in perturbation of such maps. So I'm going to take a perturbation, meaning a family of maps from C2 to C2, holomorphic. Epsilon will be a small parameter. And it's a perturbation of this map, meaning that F0 is simply F. All right, so yeah, before I forget to say it, let me apologize with those of you who might have heard a previous version of this talk. This is still work in progress, and if you stick to the talk, you will understand why it's still work in progress. So since it's we're after lunch, let me first give you, so I prepared something, okay? Let me first give you the statement of the result that we have. It's a rough statement. And then I will spend the rest of the talk in explaining to you why we are interested in this statement. Okay? Are you good? Yeah? Are you with me? Good. Okay, don't be scared. Don't be scared. Everything is okay. So the theorem that we have is the following. So now you understand why I wrote it before. Huh? So it's a long statement. So we start with a map, tangent to identity, as I was saying, at the origin, non-trivial. And we assume to have a non-degenerate characteristic direction. So this means this yellow trait here means that I will have to explain to you what I mean by this, which has director alpha satisfying this condition. The real part is at least 2. And then we can find the perturbation of F such that if this condition is satisfied, when I iterate the perturbation, the perturbed map, nj times, it converges to a map which will depend only on these 2 parameters. So I have an affine map here, x plus sigma and e to the pi q y. And I have these 2 maps, okay? So let me give names. This will be, I will get back to it, huh? Don't worry. this will be the incoming Fatou coordinate, this will be the outgoing Fatou parametrization, and B, so this convergence is local uniformly on compact subsets of the parabolic basin of F. If you know all the words that I just stated there, you can go away, okay? If you don't know them, stick to it, and you'll see all of those defined in the rest of the talk. But before going there, so why do we care? Okay, why is this interesting? Okay, so to explain to you why this is interesting, I have to go to dimension 1, because this is where the story starts.
Can we already ask questions on the theorem, or is it too early?
I would prefer that you ask a question later, if you don't mind, Romain. But if you want to ask a question, go for it. Yes, okay. So, oh yeah, let me, better? No, sorry. Better? So let me present to you the Mandelbrot set. It was already here in the in Fabrizio's talk, so he drew it. I'm lazy, so I'm using computer. So we all know the Mandelbrot set, right? So it's a set of, so the black part is a set of parameters where the orbit of 0, or the orbit of C if you'd like, is bounded, okay? So, and Fabrizio was saying in the very introduction of his talk, he was saying, oh, we can look at parameter, well, what happens when I change the parameter, okay? So I'd like to see what happens, so when I take this point over here. So let me put it here, yeah, this one, the cusp. When I see the cusp, so the cusp is C equals to 1/4. So exercise, Z squared plus 1/4 is conjugate to Z plus Z squared. So if you ever get bored, you can do the exercise. It's not a difficult one. And so what happens to the dynamics? Well, that's, by the way, in dimension 1, this is fixing the origin, tangent to the origin. Oh yes, and I forgot to write a thing in this statement that I carefully prepared before. Oh. So tangent to the identity of order 2. I will get to this order later, but now I saw it, so I had to write it down. All right, so we will get to the dynamics of this object in a second, but so you see in here that there are orbits. So I draw an orbit in this cauliflower going to what it seems to be something which is fixed in the boundary. So if you know some parabolic dynamics, you know that what I'm saying is correct. And if you don't know it, well, stick to it, and we will see it in a minute, okay? So what Fabrizio was saying is that you can converge to this point from inside the Mandelbrot set or from outside the Mandelbrot set. So let me show you pictures, it's not a proof, of what happens if I take a point. So in this little square, this is the parameter C that I chose. So in here you see an orbit which is, I'm very bad at this, which is converging to some fixed point, okay? So you still see black. So you still see orbits that have bounded orbits, okay? So these are people who are living in the field Julia set. And the boundary of the black part is the Julia set, okay? So let me choose C equals to 1/4 minus 0.01. So I'm still inside the Mandelbrot set, near the cusp. And you see that it seems that we have the same behavior that we had in the first picture for Z equals to 1/4. Do you agree with me? Are you still with me? Are you already sleeping? No, it's too early for that. So if I make a zoom of that picture, what you see is that orbits accumulate somewhere, and it seems to be at fixed point, okay? So what happens if I take exactly the same perturbation, but from the other way around? If I put a plus, then there is no black anymore, okay? And if I pick an orbit where I had convergence before, you see that there seems to be a corridor. I'm now talking to those who know parabolic implosion. It seems to be a corridor where the orbit's passing, it takes a lot of time to pass through, but then it goes away fast enough, okay? So these are just pictures, and I'm going to stop with this for the pictures. So let me close this. It's an old thing, huh? All right, sorry. Sorry for the, this one, no, this one, this one. Okay, so there seems to be something going on, okay? So now let's try to understand this something that is going on. This is an old story, which goes by the name of parabolic implosion, and starts with the dynamics of this guy. So I'm going to do it quickly for you. So what happens for this map? So this is one-dimensional. So let me rewrite it like 1 plus d. So if I'm on this side, on the negative real axis, well, if I put myself in the neighborhood of the origin, I don't need this. If I put myself in the neighborhood of the origin, say this is a small neighborhood of the origin, and I put a point, I pick a point on the negative real axis, if z is negative and real, then 1 plus z is less than 1, okay? And so orbits will converge to the origin. If I take something which is on the positive real axis, then I will go away. I will go out of this neighborhood of the origin in infinitely many steps. And actually, what the Lopez-Hernanz theorem tells you so this is beginning of the 20th century, I would say something like that. So it tells you that you have two regions, one attracting region, where orbits will converge to the origin tangentially to this negative real axis, and one repelling region, sorry, I'm doing it very big, this is not intentional, okay, where actually you will go out, okay, meaning that you will be attracting for the inverse exactly like in here, okay. So this is going to be the incoming pedal, and this is going to be the outgoing pedal. Okay? So good so far? Actually, the Lopez-Hernanz theorem is telling you something more. What it's telling you is also telling you that you have a coordinate, a holomorphic injective function defined in this pedal. Actually, it's defined even more. Let me call, so I can take all the preimages if you want of this. If I'm taking a polynomial, everything is defined everywhere. So I can take the preimages and I can take the basing of attraction of 0. So all orbits will land in this pedal, okay? So this is going to be my pedal. So the cauliflower that I showed to you in the picture, which was nicer than my drawing here. So there is an incoming Fatu coordinate. So it's holomorphic injective. Sorry, it's injective on, well, let's call it holomorphic. It's injective only in the pedal, such that, so it semi-conjugates f to the translation by 1. So for all z and b, phi incoming of f of z is simply going to be equal to phi of z plus 1. And unfortunately, the outgoing part is coming here. There is also, well, the same is true if you consider f inverse. If you consider f inverse, it's going to be written like f minus z squared plus I other term. This is not going to be a polynomial. This is only going to be defined in the neighborhood of the origin. Fine. But you can do the same exact thing, and you will have a an outgoing for true coordinate. The problem is that this is only locally defined, okay? What is globally defined, it's its inverse. So let me do it the other way around. There is also phi outgoing from C to C. So the outgoing for two parameterization. And it's semi-conjugating, again, with the translation by 1, meaning that phi outgoing of z plus 1, it's equal to f of psi outgoing of z. Okay? All right. So now what happens if I perturb this situation? So this is super classical. What happens if I consider, say, g epsilon of z, which is z plus z squared, let's write it minus epsilon squared with epsilon, which is real and positive. Can you do the computation? I mean, in here, it's easy. I can compute the fixed point. Again, exercise. So the fixed points are, do you know who they are? I have a good student in the class. Good. So fixed points are plus or minus epsilon. And what do we look if we want to understand the dynamics near these two fixed points? We look at the multipliers, okay? If I put the multiplier, did I do it? Sorry? No, sorry, I'm doing first so he knows it, okay? So I'm first doing the coupling like this, okay? And now I will do the coupling in the other direction. If you didn't understand what I just did, it's fine. So so I'm going to see what happens at the derivative at these 2 points, and the derivative will be 1 plus or minus 2 epsilon, okay? So one of these fixed points is slightly attracting, the other one is slightly repelling. So what's happening is what you were seeing before, right? There is an attracting region, and now I got a honest repelling fixed point. Okay? So this is not very interesting, but this is what's happening when I go towards the cusp inside the Mandelbrot set. So let's see what happens. So now let's do what Romain was saying. So let's consider f epsilon z, which is z plus z squared plus epsilon squared. Again, this is real and positive. Okay, now my fixed points are plus or minus I epsilon. And what happens if I consider the derivative at these fixed points? 1 plus or minus 2I epsilon. So if I now look at the modulus of these two multipliers, they are both slightly repelling. Okay? Do you ever bake cakes? That's a honest question, not mathematical. So if you bake a cake, sometimes you use an egg beater. So an egg beater, what does it do? It turns, well, both things are turning, and then if you look inside, you will see the dough passing through. Okay? And this is what's happening. So, okay, I'm doing pictures. So this is my point I epsilon, this is my point minus I epsilon. They are slightly repelling. If you think about it, 1 plus 2I epsilon is the approximation of the exponential of 2I epsilon. Okay, so we're almost like a rotation, a small rotation. And so this guy, well, this is pushing away the points, this is pushing away the point, and so points should pass through. Okay, this is what we saw in the picture. And this is what Lavaurs' theorem tells you. Oh yeah, here. So Lavaurs' theorem is telling to you the following. It's 1989. And what he's telling you, if you consider epsilon, which is exactly the guy that I was considering, if you'd like to, you can add a tail in z squared, well, I would say z cubed, epsilon cubed, if you'd like to, but I mean, you don't need to do it, but if you really want to be very general, go for it. Okay, if you take nj going to infinity, epsilon j tending to 0, such that nj minus pi over epsilon j is tending to sigma, which is a complex number, then you take f epsilon j, you iterate nj times, and it will converge to the Lavaurs map of phase sigma, which is simply, I take that outgoing for 2 parametrization, I compose it with the translation by sigma, and I compose it with the incoming for 2 coordinate. So what's interesting, so let me also write in here, well, locally, well, uniformly on compact set. Of the parabolic basin of f naught, okay? So was it that it's interesting here? What it's interesting is that you have a perturbation, but you can't understand what happens to the iterates by simply looking at a map. So this is the Lavaurs map of phase sigma that depends only on the first one, on f0, okay? And so, and it's what it is, this explains, so essentially, this explains how much time you need to pass from here to here. If you are using phase 0, this is correct. If you're not using phase 0, it's not completely correct, but trust me, okay? All right, so what do you use this for? So this is what's called, well, it's usually called parabolic implosion. Or parabolic bifurcation. And it has been used extensively to prove other results. Well, the first result that Lavaurs and Doisy proved with this theory was the discontinuity that we saw. So if you consider the application, the map sending epsilon to j of f epsilon, or c to j of z squared plus c, if you'd like. So it has a discontinuity at the cusp. Okay, that's what we saw, and that's how you prove it. You prove this result. But then you can also use this result to construct Julia sets with positive area. This has been done by Bouffe and Sherita. You can study the bifurcation loci like Mitsushi Shigura did and prove that it has Hausdorff dimension 2. The Mandelbrot set has Hausdorff dimension 2. You can construct endomorphisms of P2 with wandering domains. This is not what we are going to do today, but you can do it. So I hope that, like, almost half of my time has passed. I convinced those of you who are still listening to me that it's interesting to seek for a similar result in higher dimension. I mean, does a similar result hold in higher dimension? Is higher dimension really different? Is it that something weird is going to happen? So this is so natural that we're not the only, so I wrote something, but I didn't finish. Let me finish. At c equals to 1 over 4. So, now I have to, I should have done my speech while putting this up. So, I hope I convinced you that this is interesting to look at a similar result in higher dimension. Okay, so interesting that, of course, we're not the first one doing so. So let me give you some history, at least. Where did I put my history? I don't know. Yeah, here. So the first result, so higher dimension. So let's stick to dimension 2, which is where there are some known results. So you have results by Bedford, Smiley, and Weda in 2012. If you seek for the reference, it's 2017 on MathSciNet, and Desjardins. So now you know why he's so good at this, right? Ljubich. I think this was 2013, the preprint, and it got published in 2015. So they were working in the semi-attracting slash semi-parabolic case. Meaning that the origin is fixed, but the spectrum, the spectrum of the differential of f at the origin is 1 and lambda, with lambda in modulus less than 1 and different from 0, if I'm not mistaken. Okay? So I will not give you all the statements, of course, because otherwise I will not get to a more precise statement, and I still have to define all of this. But, well, this is where the seeds of this theory in higher dimension come. But if you want to have something which is truly parabolic, so in the parabolic case, you have to look at Fabrizio Bianchi. Where is he? I saw him. Yeah, here. So the paper was on arXiv in 2016 and appeared in 2019, published, where he really does parabolic implosion for parabolic maps. Okay? So, and if you want, let me do it as a statement. What we do with Lorena and Matthieu, we are generalizing his result to a more general setting. Okay, so to be able to give you his statement, I now have to tell you something about parabolic dynamics in higher dimension. You've seen, to explain to you what happens in the theory of parabolic implosion, I had to tell you what happened first for just the iteration of one map, which is a very particular case of sequence. Okay? So what happens? What happens in dimension 2? So you take your map, which is tangent to identity. It's in C2. So Z is in C2 now. How do you write it? So what did I do there? Well, over there, I wrote it like the identity plus the first nonlinear term. Okay? When you go to C2, well, you don't have just one nonlinear term. You have several nonlinear terms. But you can regroup them. Okay? So what I'm going to do is that I'm going to write Z plus H k plus 1 of Z plus etc. And so this is going to be a homogeneous polynomial maps of degree k plus 1. And so I promised to define everything. So this k plus 1 is going to be the order of f at the origin. All right? So first thing has been done. When you try to look at what happened for the dynamics of these maps near the origin, well, the first thing that you would like to do is that, do I have a flower like I had in dimension 1? So you will search for directions that are left invariant by the dynamics. And so let me give you the definition of a characteristic direction. A direction V, so a direction is something living in P1 of C, is characteristic if, okay, let me write it, H k plus 1 of V is, well, no, let me not write it like this, is equal to lambda V for some lambda complex number. And it's going to be degenerate if lambda is 0, non-degenerate otherwise. So if you like to see computations, this is how you do it, right? But what is this telling to you? You have a homogeneous polynomial map of degree k plus 1, so it induces a map on P1, okay? And what a characteristic direction is simply either a fixed point of this map or an indeterminacy point. And what we are saying in here is that we are taking a non-degenerate one, which means that we are considering a fixed point of this map when we consider its induction to P1. If you don't like P1, what is happening is that I have a complex line, so a complex plane passing through the origin, which is sent to itself by hk plus 1. And it can be that every point gives to a different point in the plane, or that everybody is smashed to 0. Okay, so that's what a characteristic direction is. And why are those so important? Well, that's a fact that if you have an orbit converging to the origin tangentially to a direction, in this situation, of course, then this direction will be characteristic. If so, you have an orbit for F converging to 0 tangentially to a direction, V, then V is characteristic. Okay, and so this is a fact, a proposition due to Hakim, I would say. And what Ekal and Hakim proved, well, actually, let me give you the precise statement that we have in dimension 2 up to now. So I think it's Ekal, Hakim, Abate, Lopez-Hernanz, Rosas. So in this case, take V characteristic direction, then there exists either a curve of fixed points tangent to V, or what's called a parabolic curve. Tangent to V. So what's a parabolic curve? Well, let me give you a picture. So imagine this is my characteristic direction. So if I was working with products of maps, that would be very easy, okay? If I have a product of a parabolic function in dimension 1, another one, and I combine the two, okay? So I have the pedals of that parabolic function, okay? In here, I have this direction, this is CV, and what I'm saying is that maybe I will not have what I would hope for, meaning my pedal here. What I will have is something which is a curve, a complex curve. tangential to this direction. And actually, it's even tangential to a real half direction inside the complex direction. So a parabolic curve, let me give you a definition because I will need it later. So parabolic curve means it's the image. Oh, everything is called phi. I'm sorry about that. Let's call it phi like this. From D to C2, injective holomorphic. Okay, such that phi, so the image of the disk is F invariant. It extends continuously to 1, and phi of 1 is the origin in C2. And moreover, what we have is that if you take F, you restrict it to the parabolic curve, and you iterate, then you will convert to 0, and you will do it in the direction of V. Okay, are you still with me? I know it's a lot of things to get inside, but you still have at least 15 minutes with me, so, well, it's long. Okay, fine. But the problem is that when you go to higher dimension, so you will have parabolic curves which are attracting and attached to the same parabolic, characteristic direction. You will also have repelling ones. The main problem is that these guys do not intersect in general. If they did intersect, that you would have something passing through the origin. And in general, you don't have a holomorphic curve passing through the origin. That's the main point. So if you want to have parabolic implosion in the tangent to identity setting, you need to have open sets. Okay? You need to have honest open sets intersecting. So, well, that's where this index is coming into the picture. I'm going to use that one. Sorry, I said index, it's a director, whatever. So that's alpha that I wrote over there. So I told you we can talk about fixed points. And so we have our fixed points for hk plus 1. Actually, in our case, it will simply be h2, because we are working with order 2. And so, oh my goodness, I lost everything now. It's fine. Yeah, here. So if V is characteristic non-degenerate, then, well, you can attach to it the director. So what's the director? It's simply, okay, so you take the multiplier of V as fixed point for hk plus 1 when you see it as a map on P1, and you diminish it by 1. So that's the fastest that I can do it for you. So, and what Akim tells you in 1998 is that if the real part of this director that I'm going to call alpha is bigger than 0, then there exists a parabolic domain. At 0, tangential to V. So this is the easiest case possible. So you have your, in here, what's happening is that essentially alpha is measuring what is happening transversally to the direction. And so this condition of having real part of alpha, it depends on how you write things. Sometimes it's strictly negative. It depends on how you define stuff. But in this case, we're going to take it real part positive. If the real part is positive, then transversally to the direction, you're going to get something which is attracting. And so you will be able to prove that you have a honest two-dimensional guy where you have orbits converging to the origin. And well, in the same way, you will be also able to prove that you have a repelling one, which is still two-dimensional in this case. Yeah, you're puzzled. Okay, you're okay, fine. All right, so you see there is a first thing that you should notice is that in our result over there, we are assuming that real part of alpha, the same alpha here, is bigger than 2. So we need, that's a real hypothesis. We need it to be, so when alpha is, the bigger alpha is, the more orbits will converge tangentially to the direction. And that's something that we need, at least in our proof. Okay, I think I'm almost running out of time, so I think it's far time that I put Fabrizio result on the board. That's his. That is. I have to. Don't worry. I'll get back to it. So while it's getting to you, because I cannot do more than one board at a time, so let me tell you what Fabrizio does. So Fabrizio proves a theorem, which is not exactly the statement that you would like to have, because in Lavaurs' theorem, which is still here, for, I don't know, a chance of life, you have complete convergence. You don't have that the family is normal, okay? So what he does is that, well, okay, I'm asking you to do a lot of computations in your head fast. So what happens for F naught over there? F naught is tangent to identity. So F0 is epsilon equal to 0. When epsilon is equal to 0, what's happening here is that, it's not working, it's working, whatever. Here, there is nothing, so x squared is multiplying all these things, and y is multiplying everything downstairs. So what is happening is that he's having the two axes that are fixed, okay? And then, if you look at y equals 0, on y equals 0, you have parabolic implosion. Okay, completely. I mean, that's what's happening. And if you are in this hypothesis, then what you could prove is that you can find this, well, you have normality near y equals 0. And by using, I mean, this is a very technical result, like almost all results in parabolic implosion. You have a hard part in the proof that I'm not going to explain to you because I have 7 minutes left. But this is quite technical, and by using this result, he's able to prove discontinuity of the big Julia set, if I'm not mistaken, right? In dimension 2. So I hope that I put our statement here. Yeah, now that was the one. Yeah, okay. So that's our statement. So what does our statement do? Well, we don't fix anything anymore. So what are we doing there? Okay. So remember I told you about, do you see if I write somewhere like over there or here or whatever? So in here, well, our statement, in some sense, it's more similar to this. This is what you would like to have. But you have to pay a price. The price you pay is that you're working with stuff which is two-dimensional, so you will get a two-dimensional Lavaurs map, okay? What do we do? What we are doing, so you see over there, there is an n which is bigger than the ceiling of the real part of eta, which is eta is over there, which is actually 1 plus the director, and so on and so forth. A lot of computations there, right? But what you have to have in mind, if you want to understand the statement without passing through coordinates, is that, remember, I told you, we have this invariant pedal, okay? We have the parabolic curve. So in Fabrizio's case, the parabolic curves are fixed. I mean, he has invariant lines passing through the origin. We only have a parabolic curve. So what we are asking, and what we need to ask to take care of the second coordinate, is that, well, roughly, f preserves f0, sorry, f epsilon preserves a parabolic curve tangent to v up to big enough order. And when we consider f epsilon restricted to this parabolic curve that I'm going to call C here, which is kind of not very well defined, but whatever, has parabolic implosion. So if you think about, so this is the last 4 minutes. Now I'm only talking to the experts, okay? I know it, so I will not do the effort anymore, if ever there was any. So what's happening in here is that if you're working with direct products, you will perturb in the direction where you want to have parabolic implosion, okay? So in here, the direction where you want to have parabolic implosion is the direction that I put at 1, 0 over there to simplify my statement. So 1, 0 is the characteristic direction over there, and in there, so I want to make my perturbation there. So what we wanted, so what we hoped for was you take f of z and you add epsilon squared 1, 0, which is in the direction where you want to have parabolic implosion, when you want to prove that there is some. The problem is, when you do so, how many fixed points do you get now? 4. Okay, 4 counted with multiplicity. So you have to prove that you have 2 that are nearby plus or minus I epsilon. So there are 2 who are far away, they don't play a role, and there are 2 who are really playing a role, like they were playing a role in dimension 1. And so, well, we did a lot of computations, and in trying to prove that we had convergence, we came out with this condition, which is not exactly optimal, but almost, meaning that we did, well, we means Matthieu did numerical experiments. I'm not very good at those. And it seems that M should be, so the tangency to the parabolic curve should be at least real part of eta minus 2 or minus 1. I never know. I mean, it could be equal to minus 2 to minus 1, but for the moment we are not able to make the proof work. And so, well, we decided after proving, well, trying enough to kick it out. And, well, that's the statement we get. I think I have, well, I have 1.5 minutes, so I think I will be nice to you, and I will stop it here, and thank you very much for your attention. I should have let Matthieu ask his Romain ask his question when he went.
The question was what is Q, but now you...
Oh yes, yeah, sure. Yes, Q is over there. So Q is, so you know how it goes. When you perturb, you could have an order 1 term in the first coordinate, in epsilon. That one you can kill. But in the second coordinate, you cannot kill it. And so that's what's staying. So that's the perturbation. That comes from the fact that we have our 2 fixed points. One is close, 2 are close to plus or minus I epsilon 0. And when we put them back by a fine conjugacy to exactly plus or minus I epsilon 0, then there is a Q coming out in the picture. And you can choose any Q.
But this is 0 and the phi here. So this map will what is?
Oh yeah, sorry. Oh yeah. Oh, thank you. Oh my goodness, I forgot about it. Yes, I was so much into it that I forgot to tell you that in here, this comes plus an incoming for2 coordinate. So it's exactly what we were having before. So it's phi incoming from the parabolic domain B to, but this time C2. And you have a similar one on the repelling domain, and you take the inverse of the outgoing for2 coordinate. So you have the plus, well, same, let me use this, plus same for repelling parabolic. So the existence of the repelling parabolic domain. That's phi outgoing, and psi outgoing is simply the inverse of phi outgoing. That's what it is. Sorry, it was implicit. Yes.
In the strategy of differentiator, the construction of Julia set of positive measures, it's crucial to have parabolic inclusion. Do you think you can cook up examples which are not products in higher dimension with this thread? Now you have to do.
Well, we have to finish this to write this, and we'll see. I'm not. We didn't think about it. It's a good question. Thank you. We didn't think about it.
We can ask a simpler question with same. So what consequences do you expect?
Of this result?
Yes, of parabolic inclusion. So imagine you work with the endomorphisms of P2.
So we hope.
Possibly you can find families which satisfy this.
So we are almost. So we have an hypothesis. We have to add an hypothesis to prove that we have discontinuity for the small Julia set, not the big one. So Fabrizio has the discontinuity of the big Julia set, and then we have discontinuity of J2, but we have an hypothesis that I wrote down because, yeah, you want psi of C2 to intersect the J2 of F0. So the hypothesis we have, you want the outgoing, so the outgoing parameterization to intersect J2 of F0. Not really. And we don't know how to prove that this is true for, maybe it's not even. I mean, you're the expert. So if we have this, then we can prove, well, J2 is discontinuous. Well, whatever, you understand what I mean, huh? Yeah. That's a nice corollary. We hope to have it without the hypothesis, but, well, it's still something as a consequence.
Okay, so let's thank Jasmin again.